So this is chapter 18, video 7b. We're going to deal with nucleophilic aromatic substitution reactions in this video. Here are some learning objectives for this video. And when you are done watching this video, you should be able to work these problems from the chapter 18 problem set. The problems that you should be able to work after watching the Zoom lecture, which I'm calling video 7a, are also here. So let's go ahead and get started. So with nucleophilic aromatic substitution reactions, we now have a nucleophile that attacks the benzene ring. And this is very different than what we've seen so far in chapter 18. We've been looking at electrophilic aromatic substitution reactions where the benzene ring is serving as the nucleophile and attacking an electrophile. Okay, so for these reactions, we're going to have some type of aryl halide. And so X here is going to be a halogen. You'll see me use bromine, chlorine, and fluorine as the halogens for the aryl halide in a nucleophilic aromatic substitution reaction. We'll look at we'll see a couple of different nucleophiles that maybe look familiar to you. So you've seen hydroxide, amide, alkoxides. They'll be given to you in the form of a salt. So these are all here examples of salts. And this could be like sodium. I could give you sodium ethoxide in ethanol, or sodium methoxide in ethanol. So hopefully these look familiar. And again, this is a substitution style reaction where we are substituting the nucleophile for the halogen on the ring. There are two types of aryl halides that we're going to see undergoing nucleophilic aromatic substitution. If we have an aryl halide that has a really powerful electron withdrawing group, so the EW here stands for electron withdrawing group. So this can be something like a carbonyl group or a nitro group. Okay. And the electron withdrawing group needs to be either at the ortho position or at the para position, but not at the meta position in order for this reaction to occur. The second type of aryl halide we'll see will be one that doesn't have an electron withdrawing group. So this has no electron withdrawing group, and it can have other things on the ring, but there will be no electron withdrawing group. And so for this reaction has to be carried out usually at really high temperatures and pressures, because the electron withdrawing group here at the ortho and para positions can serve as an electron reservoir. And we'll talk more about that. Here we don't have an electron reservoir, so the mechanism for this type 2 aryl halide will be different than compared with this mechanism. What you need to have for the type 2 aryl halide is you have to have an empty ortho position. So you could have another group here, like let's say this was a methyl group, but then at least one of the ortho positions it needs to be empty, meaning that there's just a hydrogen there. So for both of these, the mechanism is not SN1 or SN2. So let's take a look at how we know that they can't be SN1 or SN2 mechanisms. So we know that aryl halides, they cannot form a carbocation, right? If I rip off a halogen here in the form of a halide, then I would have a plus charge here. We don't, this is so unstable. No, this is a big no-no, right? So it can't be SN1. So I'm gonna say, so no to SN1, right? And then for SN2, we need that backside attack to happen. And if we're talking about backside attack on a benzene ring, that's you're requiring that nucleophile to be attacking like through the ring, right? That also can't happen. So no to SN2. That'll be impossible. Okay. All right. So let's take a look at each of these types now. So with our type 1 aryl halide, this is the one that has an electron withdrawing group, either ortho or para, but not meta. And let's just make a note here. This is going to be, I wanted to draw in, this is a very polar bond here. So I'm going to draw in that bond dipole just to emphasize that. So this carbon that's on the benzene ring right here has a slight positive charge because of this electron withdrawing group here via that inductive effect. So I'm just going to make a note about that you have a partial positive charge there on that carbon. Okay. And again, in this reaction, the ring is the electrophile. And here the hydroxide is the nucleophile. I'm just going to write Nu for nucleophile. So this is a salt and it will dissociate into ions. So the hydroxide of the salt is the nucleophile, and it is going to attack this partially positive carbon here on the ring. I'm just going to use red so it's a little easier to see that we're attacking right here. And when that attack happens, then we're going to form a bond from the hydroxide oxygen to this carbon. And then we can't violate the octet rule. So what I'm going to do is go ahead and bump this pair of electrons here on this carbon that also has a partial positive charge on it initially from the nitro group. And I'm going to draw a resonance stabilized intermediate here. So what do we have? We have the chlorine attached here. I have also the hydroxide. So I've lost, this is now going to have 4 bonds on this carbon, no charge. This carbon here has a lone pair and a formal negative charge. We have our nitro group. That's a plus there. Okay. And then I still have this double bond and this double bond. So notice we haven't seen this before. We've seen lots of rhenium ions or in our sigma complex for our electrophilic aromatic substitution reactions. But this is different now. We have a carbanion, so we have a net negative charge in the benzene ring on our intermediate here. This intermediate was given a special name. It's called a Meisenheimer complex. Okay. And we can draw the other resonance contributors here for this. And what I want us to pay attention to is the fact that with the type 1 aryl halide, we have an electron withdrawing group, and it either has to be ortho or para, but not meta. And the reason that's the case is that electron withdrawing group, in this case a nitro group, is serving as an electron sink or an electron reservoir to help stabilize this intermediate. So let's see if we can understand how that's the case. So I'm going to draw another resonance hybrid here. So in addition to moving the electrons around in the ring, which I will do, I'm just going to go ahead and draw what happens if I bump this pair of electrons here. I can bump this pair of electrons up here. so that I pull the negative charge out from the ring. So when I do that, remember the atoms all remain in the same locations. So I've moved this pair of electrons here. So now I have a double bond here, no charge in the ring. My nitrogen is here. I bumped a pair of electrons up on the oxygen, so that has a formal minus charge. The nitrogen still has a formal +1 charge because it has a total of 4 bonds around it and no lone pair. So here we're seeing how the nitro group, let me do this in red, is serving as what your textbook calls an electron reservoir, or what I would call an electron dumping ground. Okay, we can quickly pull those electrons out from the ring and then leave the ring with no net charge. And this helps to stabilize this complex. Okay, and in a few minutes, when I ask you to draw the resonance contributors for if a nitro group or another electron withdrawing group, such as a carbonyl, was at a meta position, you'll see that you can't get this if the electron withdrawing group is meta. Okay, so let's continue. Let's see if I can squeeze in. I need to get in 2 more in here. I'm not sure I'll be able to do that. So I can, of course, move these around in the ring. So if I bump this down here and put that there, what do I get? So again, I'm bumping this here, putting that there, and then this remains the same. Yeah, I'm going to run out of room. Oh well. Okay, and then I'll squeeze in 1 more down here. So if I bump this here, then I have to bump this up on here. Still have this. Minus charge there. Okay. So hopefully you can recognize all 4 of these as resonance contributors. And let's come up with our final product here. So what I'm going to do is use, I'm going to take this one here. This is a nice, an easy way normally for students to understand how the chloride gets eliminated. So remember that chloride is a good leaving group, and remember that hydroxide is a never leaving group. Okay, so if I'm going to take this pair of electrons and bump it back down here, and then I have to bump this pair of electrons here. This is a never leaving group, so I'm going to go ahead and bump the chloride off, and then I get my product. Now in reality, the phenol here is weakly acidic, and so we really get phenoxide where this is ionized, and so you just add a little bit of acid to protonate it. I'm just going to draw it like this. Okay, so if I'll say that we are also adding H3O plus here to acidify this so that we have the phenol part protonated. And if you're wondering, well, what happens here? We've got the sodium and we've lost chloride. So your byproduct is sodium chloride. We're in an aqueous environment here. So I don't care if you include the byproduct. I'm just going to write down the organic product. So again, for this reaction, the electron withdrawing group must be ortho or para to the halogen in order to serve as this electron dumping ground or the electron reservoir. So what I'd like you to try now is the same idea. This time I've moved the electron dumping ground from the ortho position to the para position, and I've given you a different nucleophile, but we can quickly, so we've got sodium amide here. So the amide piece is serving as the nucleophile, and this is the organic product that you get. I want you to go ahead and draw the resonance contributors for the Benzyne Intermediate for this reaction. So you do that, and then challenge yourself to demonstrate why we can't have this reaction happen if the electron dumping ground is at the meta position, because it essentially won't be able to serve as an electron dumping ground or a reservoir, electron reservoir. And you can demonstrate that to yourself if you draw. You'll only get 3 resonance contributors here, but you should be able to demonstrate that to yourself. I'll let you do that. And let's move on. So let's look at an example now of a different electron reservoir than what we've seen so far. Let's take, we've been looking at nitro groups. Let's take a look at a carbonyl group. So, and I'll give you a different nucleophile. So this is sodium methoxide is our nucleophile here. And I'm going to go ahead and put on a carbonyl group. Let's do something like this. Okay, so I have a carbonyl carbon directly bonded there, and this is at the para position. Okay, so that's good. I'm going to do this now a little faster than drawing out all of the resonance contributors. So when on an exam, like if you're just asked to predict the product, if you want to just quickly imagine what is happening here, I can take my nucleophile and attack. Remember, this has a partial positive charge on it. Attack at this position here. And I'm going to go ahead and just bump these here, bump this here, and then bump this up here so that I can, I'll draw one of the resonance contributors. And you can go back and draw the rest if you want. But I'm just trying to, as quickly as possible, get to my product. So that's why I'm kind of just going really fast. So again, I've moved this here. I've moved this here. And this is nice because I can really quickly see, so now this has a negative charge on it, how the carbonyl is serving as an electron reservoir, because notice here that the ring doesn't have a charge. So again, you can draw 3 more resonance contributors. I'm just trying to get through this so that I can get to the product. So to do that, I'm going to go ahead and bump this pair of electrons down. Then I have to bump this down. Well, then I have to move this here. And then who's the better leaving group here? Well, the methoxide, it would be a very bad leaving group, but the halide is a good leaving group, bromide. So we'll kick that off. You get sodium bromide as your inorganic byproduct, but let's just say predict the organic, because that's what we care about. And if you want to be quick, you can just draw a circle in the ring there. So now we have, oh look, we've figured out how to put a methoxide on the ring. So remember, we were talking about how with the electrophilic aromatic substitution, we couldn't do that, but with the nucleophilic aromatic substitution, we can. Okay, so there we have our organic product. Let's do that for these examples down here, and notice that they look a little scarier, but we can do it. Let's evaluate each of these. So again, we have here an aryl halide, but we see 2 halogens. Oh my goodness. Well, we need an electron dumping ground ortho or para to it, but not meta to it. So for example, this at this position, this nitro group is meta to this, and this nitro group is meta to this. So we're not going to be carrying out, so I'm just going to write the NO2s are meta to this one. So we're not going to be kicking off this chloride. But now for this chloride, I have at the ortho position a nitro group. So ortho NO2. And then we also have one that's para. And if you're like, oh my gosh, well, there are 2 nitro groups. Is that allowed? Certainly. Remember, the point of the electron withdrawing group is to serve as an electron reservoir to help stabilize the intermediate. So if we have 2 of these, it's just going to be even more stable. So what are we going to get for our product? Okay, so here's our nucleophile is ethoxide, right? So we have a negative and a plus. So I'm going to be attacking at this carbon, right? And then I'm just going to go directly to the product here. And what do I expect to get? So you can just draw the circle in the ring. It's going to be aromatic. This is going to get kicked off, and you're going to replace it with this ethoxide, right? This is still here. This is still here. This is still here. Okay, so I know I didn't show you the mechanism here. I'm just coming up with the product. Okay, and then let's try this one down here. Also looks a little scary, but let's just break it down. So we have, first I recognize a strong nucleophile, right? My methoxide. Okay, I have an aryl halide here, and I have ortho to it, so nothing on this side. Ortho here, I have a carbonyl group. Okay, so let's investigate then if I go ahead and attack. It's red here. I'm gonna attack here, and I'll go ahead, I'll draw one of the resonance contributors just so you can kind of see this. So I'm gonna flip this over here and bump this up. So let me draw. So now we have that. So remember, this is serving as an electron dumping ground, or an electron reservoir. That sounds so much classier, right? And then what do we have here? We still have our chlorine, and now we have the methoxide. Okay. And we still have this, we still have this, and we still have this. And I just want to make a note about something right now. So notice here that technically at this meta position, we have an electron withdrawing group as well. The reaction, though, we don't say like, oh, the reaction doesn't happen because there's an electron withdrawing group at the meta position. No, as long as we have an electron withdrawing group at the ortho or the para, we can make this go. So it doesn't matter here that there is something at the meta position. It's just that this isn't going to, we wouldn't expect it to serve normally. If we have an electron withdrawing group at the meta position, we don't think it's gonna serve as an electron reservoir. Okay, so so here is one of my resonance contributors, and I like to show this one because then I can get quickly to the product. So if I take this and bump it back down, and then I bump this back here, I'm going to lose that chloride. If you want to be lazy and just go zoop, you can do that. Okay. All right. So, so these are some examples of the nucleophilic aromatic substitution with the type 1 aryl halide. So now let's take a look at the type 2. So the type 2 aryl halide, doesn't have an electron withdrawing group on it. It could have other groups on it, but it doesn't have an electron withdrawing group on it. So it doesn't have an electron reservoir to help stabilize the intermediate. So this means then that we're going to go through a really high energy intermediate. And so this is going to force us to do this at really high temperatures and pressures. And just a little side note, this mechanism was figured out at the Dow Chemical Company by a group of chemists. And it's kind of an interesting story. You can read a little bit about it in your textbook that interests you. So you don't need to memorize these conditions here. So this is a really high temperature. This is like 650 degrees Fahrenheit. It's really high pressure. And I'm mentioning here that we're adding acid as a second step because the hydroxide would be in the form of alkoxide, since this is weakly acidic. So we just acidify this so that we protonate that. So here we don't have an electron withdrawing group. We get, in this case, our nucleophile was hydroxide. So we're making phenol here. And the inorganic byproduct, which I don't care about, is the sodium chloride. So this reaction mechanism is really interesting. I'm going to go ahead and tell you the name of it. It's called Elimination Edition. And so we have a two-step process where in the first step we see elimination, and then in the second step we see addition. So in the first step of the mechanism, I'm doing this one here and I'm just writing out our nucleophile, the hydroxide here, is attacking. So you need, remember with the type 2 aryl halide, you need at least one ortho position empty. And by empty, meaning there's just a hydrogen there. So we're going to attack a hydrogen that is ortho to the halide, to the aryl halide. I'm going to bump, I know you're going to scream, this pair of electrons here, start screaming. And then we're going to be losing the halide, okay? So this is an elimination step. And what do we end up with? We end up with this high energy, extremely unstable intermediate that, yes, I really am drawing a triple bond here. Now, it's not a triple bond in the true sense of it. This is more like a diradical than a triple bond. So you actually have sp2 orbitals overlapping, which I know you're going to yell about also because you're like, it should be sp. But anyway, I want you to know, this is the name of this intermediate. It's called a Benzyne Intermediate, and it is very reactive. Why? Because it's very unstable. Okay, so in the second step, we're going to see the addition, and here using water. Splitting that up into OH and H, okay? So if you're scratching your head saying, is she crazy? You would not be alone. When this mechanism was first hypothesized, I mean, the chemists it was a joke, okay? Like so many things and new ideas in science, it was initially mocked openly, okay? So people thought it was just totally ridiculous. I'm going to walk you through one of the experiments that helped to support this mechanism. And if you want to learn about some of the other experiments, your textbook goes into more detail about the Diels-Alder trapping experiment that also supports this mechanism. I'm not going to talk about that or require you to know anything about it. But I think the isotopic labeling experiment is really elegant and easy to understand. So I'm going to walk you through that. So the most abundant isotope of carbon is carbon-12, as you probably know. So what chemists did is they went and made an aryl halide with a far less abundant isotope of carbon, carbon-14. And so I'm labeling that carbon-14 here with this asterisk. Here we're using the salt potassium amide. The amide piece is the nucleophile, okay? And it is going to attack the proton that is ortho to the halogen on the benzene ring. And then if the hypothesis is correct, we're going to expect, in the hypothesis of the mechanism, we're going to expect to see both of these products. So I'm going to bump this down here. And again, we have our elimination to make our benzyne intermediate. Okay, if you want to put brackets around that, fine. And then in the next step, I'm using ammonia. So in your textbook, they'll say liquid ammonia, fine. This is the addition piece where you're going to have a hydrogen going to one carbon here, and then the NH2 to the other. And so what happened when they did this experiment is they did indeed get a 50-50 mixture of these two compounds, which supports this mechanism, okay? Because if we didn't get this intermediate, if it was something that happened all together in one step, we would expect just one product. So that's kind of elegant, and so I just wanted to mention that. So something that you'll have to be able to do on your next exam is to be able to identify any compounds that cannot undergo nucleophilic aromatic substitution through a benzyne intermediate. So let me just show you an example of that. So here we have an aryl halide, and we don't have an electron withdrawing group at the ortho or para position. So if we're going to have this undergo nucleophilic aromatic substitution, it'll be type 2, meaning we need a benzyne intermediate. But this can't undergo a type 2 style NAS reaction because the ortho position is not empty. We don't have at least one ortho position empty. Both of the ortho positions here have methyl groups on them, so this won't work, okay? So again, we need to have at least one hydrogen in the ortho position in order for the NAS through a benzyne intermediate to happen. Okay, so that's one thing you need to be able to recognize. Another thing you need to be able to do on your next exam is to draw the structure of the benzyne intermediate, if the reaction can happen, as well as the product or products if there's more than one. And I will let you know how many that there should be. Okay, so let's go ahead and practice this. I'm gonna go ahead and I'll just go like this. There we go. So I'm gonna fill in. So here I have at this ortho position. So I'm going to attack here, and my benzyne intermediate is this, right? And then in the second step, I have here my addition of the ammonia. So I can add an H here and an NH2 here. And then I can also do it the other way around. So if I add my H here, my NH2 here, and if you don't want to write this hydrogen, that's fine. And then I can also get, if you want to be lazy like me, just put a circle in there. I can also get this. So notice here we're putting an amino group directly on the ring. Here, there's a hydrogen there. Okay, so now let's try this one here. Let's put our benzyne intermediates down here, and I've got two spots for them because we've got two that we can make. Why? So because of this, we've got two different ortho protons. So if I do this, I get as my intermediate Still have this there. And now I have this here. So I can get this, or if I took off this one, then I have, and I'm gonna just move these around. So if I move this one, let me fix this. Hopefully you're watching this now and saying, oh, this is a good teachable moment, Alicia. So remember, if I do it from the other side, I'm just gonna draw it like this. Remember, this is a benzene ring, right? There's resonance. CH3. So if I'm ripping off this one, okay, so what do I get here? So now I have my benzyne intermediate like that. CH3. I've lost that. What am I missing here? I'm missing this double bond and this double bond. Okay, and then what are all of my possible products? So in the second step now we're adding water, so an H to one carbon of the triple bond, and then the OH to the other, and then this gets reduced to a double bond. So, and again, be kind to yourself by right away just filling this out and filling in this piece. So that's going to be there on all of them. Okay, so starting with this, if I add the H here and then the OH here, the phenol is para to the methyl group. All right, let's flip it around. What if I add my OH here and the H here? H there, okay. Now what about this? If I add the H here, I get the OH meta to this, that's that product. Or if I put the OH here, now I can get this also. And then the H there. So those are my three. Okay, oh, I need to do office hours now, let's stop.